Hello and welcome to another episode of Isn't That Something? You know, in uncertain times like these, we find ourselves asking questions we may never have thought we'd ask. Today, let's explore one of those questions. Are your ears gills? Yes! Wait a minute, what? Every time I've tried to breathe underwater through my ears, I've failed. If you can't breathe through your ears underwater, then how is it that your ears are gills? Well, the story starts a long time ago, in the heady days of the Cambrian explosion, some 570 million years ago. Our worm-like ancestors split from their fellow deuterostomes and started a new band called the Chordates. The rest of the deuterostomes went on to become stars in their own right, so don't feel too bad for them. Among animals, outside of sponges, jellies, and placozoa, there are two major groups, in this case, superphyla. On the one hand, we have deuterostomes, like us vertebrates and the sea stars and a couple others. On the other hand, we have protostomes, which include arthropods, mollusks, earthworms, and the wildly overrated tardigrades, or water bears. A quick aside about tardigrades, if they're so great, how come they get eaten by snails so much? How'd they even get the nickname water bear? Did we just forget about polar bears? What's the use of being able to survive the vacuum of space if you literally have 0 rockets? Anyway, the biggest difference between deuterostomes and protostomes is seen in the very early development of the embryo. When an embryo is just a little ball of cells, it's called a blastula. At some point, part of the blastula folds inwards, forming a chamber that goes on to become the gut. And the opening of this chamber is called the blastopore. In protostomes, the blastopore goes on to become the mouth of the creature. In deuterostomes, like us, the blastopore goes on to become the anus. That's right, your very first well-defined body part was your butthole. Wow. Unlike other phyla, the chordates had certain unique and defining characteristics, or synapomorphies, that set them apart from the rest of the animals. We unlocked the notochord, a stiff cartilaginous rod that helps define bilateral symmetry, gives structure and a place for muscles to attach, and in many of us matures into part of our intervertebral discs. The chordates also acquired a dorsal nerve cord. Unlike the ventral nerve cord of some invertebrates, the dorsal nerve cord develops on the dorsal or back region of the animal. You might know your own dorsal nerve cord as your spinal cord. Or maybe you give it a different name. Leave a comment letting us know what you call your dorsal nerve cord below. The third of 5 chordate synapomorphies that I'll mention is the endostyle, a mucus-producing organ in the pharynx that helped our early ancestors with filter feeding. Now you might pause here and think to yourself, I don't use an endostyle for filter feeding. Am I a real chordate? Yes, you are, but your endostyle has a new job in your neck as the charismatic and charming thyroid gland. Another chordate synapomorphy is the post-anal tail. Have you ever watched an earthworm poop? It comes right out of the end of its tail. Magic. Now, watch a cat poop. Note that it does not come out of the end of the tail. Isn't that something? The last chordate synapomorphy is the one we need to focus on: pharyngeal slits. These slits seem to have first arisen in the early invertebrate chordates to facilitate filter feeding. Again, you might think to yourself, I don't have colander-like slits in my neck to facilitate filter feeding. Not anymore, you don't. But go back far enough in your life, like when you were just a little peanut in your mom's womb, and you would see gill-like structures on your neck. Of course, these do not develop into full-blown gills for most people outside of Kevin Costner. Before we explore pharyngeal slits any further, we need to go back in time to the Cambrian explosion. Back in these days, our friends, the chordates, were all flippy-floppy, not a bone in their body. But at some point, somebody decided to grow a spine, and actually grow a spine. Thus, the vertebrates emerged. These early vertebrates also decided that it would be good to have skulls. so they grew those too, becoming craniates. Today, all craniates are vertebrates, and all vertebrates are craniates. So, evolutionary biologists consider the terms synonymous. If you want to sound all fancy pants, say craniates, or get Latin with it and go full-blown craniata. But if you want to be a down-to-earth biologist of the people, say vertebrates, or bone gang. The early vertebrates lacked jaws, having circular rows of spiky teeth, arranged to allow them to kiss things to death. Today's lampreys and hagfish retain this jawless setup, and can be seen in the deep ocean and in your nightmares. One structure that jawless fish do have, however, is gill arches. These bony structures help to support the gills, which are a derived form of pharyngeal slit. Each gill slit is associated with a bony arch structure. By flexing and articulating these arches, jawless fish learn to suck more than any other animal in the Cambrian seas. By the time of the Ordovician period, a mere 450 million years ago, the first gill arch of some vertebrates had gotten so good at flexing that it became able to chomp stuff, and thus the jaw was born. These jawed fishes are called gnathostomes, and, spoiler alert, you are a gnathostome. If a gill arch became the jaw bones, then what happened to the gill slit in front of it? Great question. It became trapped and isolated from the other gills. It can still be seen in animals like sharks and rays as the spiracle. In tetrapods, that is, four-limbed animals like amphibians, reptiles, birds, and mammals, it became the ear hole. See, your ears really are gills. Not only is your ear hole a highly modified gill, but the bones in your middle ear are a derived form of the jaw bones of fish. The three mammalian ear bones known as the malleus, incus, and stapes, or hammer, anvil, and stirrup, are all derived forms of fishy jaw bones. Fish ears are mostly used for balance, sensing the orientation in space of the creature, while detection of sound is done primarily by the lateral line, a long row of sensitive cells along the side of the fish that's no longer present beyond the embryo stage in us landlubbing tetrapods. Arr. Since we live in air, it's a bit tricky to conduct sound into our fluid-filled inner ears, where our sound-sensitive hair cells, not actual hairs, live inside a snail. It's not an actual snail, but the cochlea gets its name from the Greek
Cochleas,
meaning spiral snail shell. To get vibrations into the cochlea, the middle ear bones act like levers to apply a mechanical advantage in conducting sound energy from the vibrating eardrum or tympanum to the oval-shaped window opening, known as the oval window, connecting the stapes bone to the cochlea. The evolution, structure, and function of the inner ear are fascinating topics in their own right and deserve their own video. When structures in the anatomy of an animal are derived from structures in basal ancestors with different function and/or appearance, it is an example of homology. The human body is full of all sorts of fun homologies with our fishy ancestors. Of course, our arms and legs are homologous to the pectoral and pelvic fins of fish. Our teeth are thought to be homologous to early armored fish scales. In fact, the tiny, tooth-like skin projections on sharks are known as denticles, or little teeth. This is why, if you pet a shark the wrong way, it kind of feels like a cat tongue, although it should be noted that the spiny papillae on a feline tongue are made of keratin, and so are more similar to hair or claws than teeth. Speaking of claws, as we learned in Isn't That Thumb Thing, human nails are homologous to claws. At the molecular level, human chromosome 2, one of 23 pairs of chromosomes found in all of our somatic cells, is homologous to two different chromosomes found in apes like chimpanzees and gorillas that fuse together end to end deep in our past. When we look closely at chromosome 2, we can even see a deactivated centromere, sort of the belly button of the chromosome. Even within a single species, homologous structures can be found. There are anatomical differences between biologically male and female humans, but often those differences arise in characteristics that develop from the same embryonic structures. The ovaries and testes are homologous, for example, as are most reproductive structures. I'll let you do that particular Google search on your own time. The evolution and development of the vertebrates, as well as life on Earth in general, is one of the most compelling true stories in the universe, and there are lifetimes of knowledge to be gained from its study. Many chapters of this story are well understood, and many more are left to be uncovered by present and future scientists. Next time you put earbuds in, remember you're really piping sound into your gills, and think, isn't that something? Isn't That Something was written, recorded, and edited by me, Ralph Crewe. Original music provided by Kyle Simpson. Lamont Craven is new to the team as Director of Marketing and Communications. If you enjoyed this video, please like, subscribe, and squish the bell. If you really like this video, please share it with everybody that you've ever met. Thanks for watching, and remember, explore the world responsibly.
Isn't that something? Isn't that something?